So the standard deviation of the residuals is exactly what it sounds like. We take all of our residuals, we make them a list, like if we look at this pattern above. So if we had all of our residuals and calculated their standard deviation, just like they were any set of data, we'd have the standard deviation of the residuals. It's important to have this because it will tell you that typical or average prediction error. So it doesn't quite work if we just add up all the residuals, because from a least squares regression, our residuals should always add up to 0. So that doesn't really tell me the average distance, whereas standard deviation does. So it gives you the typical or the average residual, or the residual is basically what it does. So that's kind of it in English. It has this little, how would you say this in English portion. I don't know that we really need that, but I will give you what I wrote down. Okay. So this is the standard deviation of the residuals, is the average or typical residual value. So this value is also known. So one thing I would like you to remember is this, oh, that was interesting. This value is also sometimes known as the standard error. So a standard error is also a standard deviation. Later in the year we'll find out what the real difference between those two is. But it's basically calling the amount we were off from the regression line an error. So that's another name for a residual, is how far were we away. So the standard or the average error is the standard deviation of the residuals. All right, let's go ahead and move to the next page. We're already on page 5, but it's going to take us 2 videos to get through this. So let's just run down the role of R-squared. So what is R-squared? It literally is you take your R, or your correlation, and you square it, and you get this value called R-squared. It is tied to that least squared regression. So if R is a form of almost just a standard deviation of our line, remember we just did standard deviation of the residuals, then R-squared would be like the variation. It would be kind of the average of all of those squares that we created around our residuals. So this is where it's coming from. So the better fit we can make all of those little squares, the more data we can capture with our regression line. So let's take a look at what's going to go in the blanks here. So in this first one, the coefficient of determination. So this one has a crazy name. Coefficient of determination. I don't know why it almost sounds like it's a superhero power. Don't worry, I'll save you with the coefficient of determination. Yes. Dun da da da. I don't know why. It's just this dramatic sounding term, but it's really just R-squared. So it's the fraction of the variation in the values of y that is accounted for by the least square regression line of y on x. Okay, so we can calculate it using this formula. I don't think this formula is on your formula sheet, but that's okay. All right, so it says where SSE is the sum of the residuals squared. So this is basically the sum of your least squares. So all those little squares we created, the least they could be, the smallest they could be, it's the sum. And that's what our calculator was giving us when we did that activity together, was the sum of squares, or sum of the least squares. So that's SSE. And then this one, this is almost, it's like one step away from that standard deviation of our residuals. So it's really close. All right, so see how this says super important? It really is. All right, so what's next to that? All right, so I'm just going to make this really pretty. Every time you're asked to interpret the meaning of R-squared, just memorize this line. It'll make sense in a moment. You can use the same response. So blank percent of the variation in blank response variable name is accounted for by the regression line. All right, so I'm going to show you how to actually use that term in the next video, so how to use that sentence, and it will make a little bit more sense.